This is lecture number 14. We are going to circle back a bit and look at complex power. When we're done, we'll have an understanding of what P, Q, and S are. Before we start, I'd like to do a quick review of the transformers. This is transformer T1, transformer T2. We'll let this wire resistance be 500 milliohms, and we'll let the return be 500 milliohms. This is a 1 to 10. We call that a step-up transformer. And we'll let this transformer, this T2, be a 10 to 1. And we'd call that a step-down transformer. On the load side, we have 80 kilowatts. And that load is designed to operate when the voltage on the secondary of T2 is 277 volts. We'll assume an ideal transformer which has no loss, and you can see that this is a pure resistive load, and it's pure resistive on the wires that connect the two transformers together. We start this problem at this point right here, where we say the current in the secondary of T2 is equal to a power, it's 80 kW, over a voltage, which is 277. That gives you about 290 amps. So that would be 80,000, or you could go 80 and then use this 10x10 button. Oops, and then a 3. Right, so same thing. And that's all divided by 277, which gives us the 290 amps. And we also know that the voltage on the secondary of T2 is 277 because it says so right there. At this point, we can move to the primary of T2. So the current on the primary of T2 is equal to this divided by 10. And you may recall that the turns ratio, so N primary over the number of turns on the secondary, is the voltage primary over the voltage secondary. And then we have the current, which is upside down. So it's the current on the secondary over the current on the primary. For T2, that becomes 10 to 1. And then we're talking about the current. So the current on the secondary is 290 amps over the current on the primary. If you cross multiply, you would say that 10 times the current on the primary is equal to 290. Therefore, the current on the primary is simply 29 amps. We can bring that over here. So the current on the primary of T2 is 29 amps. And the voltage on the primary of T2 is going to be this multiplied by 10, so 2770 volts. Now, the last time we met, we really focused in on the power lost aspects of this circuit. So we can talk about power lost is equal to I squared R, which in this case is 29 amps squared by a resistance. So we have 500 milliohms and 500 milliohms. You put those together and that's 1 ohm. So the power lost is 29 times 29. That's about 840 watts. While we're here, we may as well finish the problem. So the voltage on the secondary of T1 is going to be this here, so that 2770 plus the voltage drop across the resistors. So that voltage drop is 29 amps by 1 ohm. The final step of this problem is to calculate the voltage on the primary of the T1. So the voltage on the primary of T1, because it is a 1 to 10 step down, will be 1/10 of that 2800, so just 280 volts. This is a fine problem to get us started, but it assumes that we're dealing with a pure resistive load. And it turns out in the real world that most loads are not pure resistive. Most are, in fact, inductive. Here's a typical example. You could consider this the model for a 1 horsepower single-phase motor. With the tools we already have, we would calculate the impedance as 9.6 plus J 7.2. That would be ohms. From there, we could calculate the source current, which in this case is a voltage over that impedance. (120) divided by 9.6 plus 7.2 J. Close that parenthesis and shift it into polar form, please. So that's 10 amps at a phase angle of -37. So the current that flows in this series circuit is 10 amps at a phase angle of -37 degrees. We should remind ourselves of something we said earlier, and that is that most loads are inductive. Now, that doesn't mean that the load looks like an inductor. That means that the load looks something like this. We are actually dealing with a resistive inductive load, or an RL circuit, just as you've got here. You've got L1 and R1. Since this discussion is about power, we may as well get started. We can talk about power in the DC world as pi. We said power is equal to the product of a current and a voltage, and that served us well. However, it doesn't work when we have current vectors, so we need to modify this. In the AC world, this equation becomes S is the product of the complex conjugate of I multiplied by the voltage vector. So that's complex power. This is the voltage vector. And this is the complex conjugate of current. And just what do we mean by the word complex conjugate? It goes something like this. If we have a vector in the real imaginary plane, so say the vector looks like that, to take the complex conjugate of that is to flip it about the real axis. So that vector becomes this vector. So all we've done is flip the sign. For example, 5 at a phase angle of 45 becomes a complex conjugate of 5 at a phase angle of -45. So if this is current here, the complex conjugate of current has a different sign. And it works the same way in polar form. So 2 plus J3 becomes 2 minus J3. Okay, again, all we're doing is we're flipping about the real axis. So now we can go back to our problem here, where we had a current of 10 amps at an angle of -37, and we had a voltage of 120. And that's all we need to push through this equation to find what our complex power is for this motor. Complex power, S, is equal to the complex conjugate of the current by the voltage vector. And our current was 10 amps at a phase angle of -37, and our voltage was 120 volts at a phase angle of 0 degrees. Now, I just made a mistake. Do you see it? And the answer is we're supposed to use the complex conjugate of current. And I mistakenly wrote this with the wrong sign. So you notice here that it's 10 at an angle of -37, which means the complex conjugate is going to be 10 at an angle of 37. We can solve for this as 10 at a phase angle of 37 multiplied by 120, which gives us about 960 plus J720, and the units for complex power are volt amperes, or just VA. While we're here, we can also express this in polar form, which gives us 1200 volt amps at a phase angle of 37 degrees. If we sketch that out, we end up with something called a power triangle, where this is 1200 VA. This is the angle theta, which in this case is 37 degrees. Down here, we have real power in watts. And here we have 720 what are called VARs. We would call this piece the apparent power. We would call this very important piece the real power. And this piece we call the reactive power. Just as a side note, this real power is what is associated with our power flow diagrams. So in this particular circuit, we had 960 watts as power in to our motor. Right, if we were to go back here, we would look at this and we would say, based on our current and voltage, there were 960 real watts that went into this motor. We had a power output, which is mechanical power, and we had this piece, which was power lost. Together, the mechanical power and the power lost is equal to the power in. Again, that's the real piece. The VARs is kind of interesting. That's the power that is used and stored in the reactive components. In this case, it's an inductor. So you remember an inductor stores energy in that magnetic field. And what's happening is that on every half cycle, the magnetic energy in that inductor is first charged, and then it's delivered back to the power grid, and then it's charged up in the opposite polarity. So you end up with energy that's flowing back and forth between the inductor, right, between the inductance of the motor and the generator itself. That reactive power does not do real work. It's in the imaginary plane. It's reactive. It's imaginary power. It's power that does no useful work. Actually, we should move that statement back just a little bit, because when we're talking about reactive power, we're talking about the energy that's stored in the magnetic field. And when we get to motors, you'll see that it's the magnetic field that actually allows the motor to function. So you could argue that without reactive power, there would be no magnetic field. Without a magnetic field, there would be no motor. While you're adding terms to your note card, you might want to add this one. It's called power factor. And that describes the amount of apparent power that becomes real power. Another way of saying that is power factor is a ratio between the apparent power and the real power. For shorthand, you would say the power factor is equal to cosine of theta. So in our particular example, we are dealing with the cosine of an angle of 37 degrees. So there's the 37 degrees. And you enter that to calculator, you go cosine of 37. And that gives us a power factor of about 0.8. Or you could also express that as a percentage. So you could say it's 80%. I should mention that when you're talking about power factor, you should specify whether it's inductive or capacitive. In this particular example, it was inductive. We can write this a different way. In our example, 1200 was the apparent power multiplied by the power factor will equal the real power of 960. Again, this was the apparent power. This was the power factor. And this was the real power. This is a good time to look at those trig properties again. So sine theta, cosine theta, tangent theta, opposite hypotenuse, adjacent hypotenuse, opposite over adjacent. And what we're talking about is this one right here. When we talk about power factor, you're really talking about the relationship between the adjacent and the hypotenuse. With that said, we should go back here and scratch relationship and say that power factor is the ratio between apparent power and real power. And again, you can use it like it's shown here. All right, so that was a very quick first pass through the concepts of complex power. Let's take another pass through this topic. This time we'll pick up some of the finer details. So the rules for complex power. One of the first things we would say is that complex power is additive. Let's first consider this circuit. We have a power source on this side, and then we have a series parallel connected load. Since power is additive, the source power is equal to 10 plus 500, so there's the 10, there's the 500, plus 300, plus 1,000, so 300, 1,000. So our power at the source is equal to 1810 watts. I think you would agree with that statement. If not, consider this. Suppose each block represented a resistive load connected in a series parallel circuit. Well, each resistor would be giving off a certain amount of heat. The total amount of heat given off would be represented by the total power of the circuit. Again, so we could say that power is additive. Now we can look at a slightly more complicated circuit dealing with complex power. So suppose we had 500 plus J100 volt amps as our first load. And then we had 2 kW with a power factor equal to 0.8, and that power factor is inductive. So now we have a system with 2 complex loads. To get us started, we should draw the power triangle for each load. So for the first one, we have 500 real and J100 reactive. The second load may also be described as a power triangle. This time we're told that there are 2,000 real watts. I should have put units in over here, so we have watts there, and these are vars. The angle is described by power factor is equal to 0.8. So you remember that cosine of theta is equal to the power factor. And this time we're told that cosine theta is equal to 0.8. Now, to solve for theta, you need to run it through the arc cosine machine. So inverse cosine of cosine theta is equal to the inverse cosine of 0.8. 8. Do y'all remember when we talked about the speeches? And we had one machine that would take stars off and another machine that would put stars on. And it didn't really matter which machine you went through. As long as you went through both machines, you would end up back where you started. Well, that's what's going on here. So if you take the cosine of theta and you run it through an inverse cosine machine, you end up with just theta. And then as far as the 0.8 is concerned, shift cosine 0.8 close paren is equal to about 37 degrees. So that gets us a little closer. Now, we also said that power factor was the ratio of the hypotenuse to the adjacent side, which means you could take the number 2000 and divide it by 0.8, which gives you 2500 VA. And the last step in order to find the vars is you need to use more trigonometry, or you could use the Pythagorean theorem. We talk about a b squared, or just a b is equal to the root of c squared minus a squared. In this case, this is equal to 2500 squared minus 2000 squared, and then you take the root of that. So 2500 squared minus 2000 squared equals, and then you take the square root of that. So square root of answer is equal to 1500. So that's 1500 vars. Now that that's done, we can go back to our original question, and that is, how do you calculate the total power of this circuit? We said power is additive, but what we also need to recognize is that we can add the real pieces together, and we can add the imaginary pieces together with no problems at all. So the total power is equal to the real pieces, so 500 plus 2000, and then we add the imaginary pieces, plus J100 plus J1500, and that works out to power total, a real piece of 2500 plus J1600, and all that is volt amps. With the understanding that this piece is real power, and this piece is reactive power. While we're on the subject of power triangles, I wanted to show you something. If your power triangle looks like this, we could talk about that being a resistive inductive circuit. So that would be a RL circuit. And this triangle is upright. Not to be confused with this power triangle, which is for capacitive circuits. So resistive capacitive circuits. So RC. Again, RL, the power triangle, is positive, right? This angle here, this angle theta, is positive. For an RC circuit, the angle is negative. Something to realize here. Since total power is additive, right? Since we can add the real pieces, and since we can add the imaginary pieces together, you can see if one power triangle points up, you have another power triangle that points down, the capacitor and inductor basically undo each other. Before our talk is over, I'll give you a clear example about what that means. Let's take another look at the power triangle. We already mentioned this was the real power. What we didn't mention is that the real power has units of watts. In DC circuits, that's the way it was as well. You talked about power in watts. When we're dealing with AC circuits, we would have power, the real power described with a unit of P for power. We talked about the hypotenuse being the apparent power, units of volt amps, and it has a symbol of S. And finally, we have reactive power, units of vars, and a symbol of Q. We should make a few notes here. This reactive power is power that flows back and forth between the generator and the inductor or capacitor, depending on what type of circuit you have. Real power is the power that actually does work. A few examples are light, the mechanical output from a motor. It also includes other things that you might not consider work, such as the I squared R losses in a wire or in the windings of a motor. You could think of these I squared R losses as heat, and it takes real work to heat something up. So that's our definition there. Apparent power takes a little bit more work to define. We need a circuit to explore what it means. Let the source be 277 volts at a phase angle of 0 degrees. Let this be 25 J12. We'll put a meter here, but we already know what that's going to read. Of course, it'll read 277 volts. And our current meter will read 10 amps. Again, so this is just an example, and we're going to use it to explore what we mean by apparent power. If I was to use this meter and I measured the voltage, the meter would read 277 volts. If I were to reconfigure the meter by moving the probes around and measure the current would read 10 amps. Again, that's an RMS voltage and an RMS current. If you multiplied those together, you would say S is equal to volts times amps, which is 277 by 10, which gives us an apparent power of 2,770 VA. You'll notice these are not watts. We've been so used to expressing power in watts, but that's not what this is. In this case, the apparent power, which is to say the power as measured using a conventional meter, would suggest that it's 2,770. Notice that I did not put a bar over the top of S. This is not a vector. I suppose we could try to put a power triangle together. The only thing we know is that the length of the hypotenuse here is 2,770 volt amps. That is all we know. And that's all a meter such as this can actually tell you. It can only tell you apparent power. Now we could add another note here that simple meters do not know angles. If we were to complete this power triangle, we would need one of two methods. In the first method, we would have to know something about the circuit. And the other method is to use a power analyzer. In this example, we do know a great deal about the circuit because we know the impedance of the circuit. So the impedance in this case is 25 plus J12. And we also know the voltage is 277 volts. So we come down here. The impedance is 25 plus J12. We can measure or calculate the current as 277 over 25 plus J12. That gives a current of 277 divided by 25 plus 12J. put that into polar form. So that's about 10 amps at a phase angle of negative 26 degrees. By the way, that was something we knew up here, wasn't it? There it is. We knew this was 10 amps before. We just didn't know which angle it was at. So it's 10 amps at an angle of negative 26. The complex power, S, can be computed as the complex conjugate of I by the voltage. In this case, current is 10, but we want the complex conjugate of that, so to be 10 angle 26. And our voltage was 277. So we go 10 at an angle of 26 by 277, which gives us about 2500 plus J1200. That's volt amps. We could also put that into polar form, which gives us 2770 VA at an angle of 26 degrees. This is where we get really fussy with our terms. This is complex power. It is a vector. It has a hat. This is a scalar for complex power. 2770 volt amps, but it doesn't have a direction. All it does is it has a magnitude. Again, there's no bar over this thing. Power. In this case, power is 2500 watts, and Q is 1200 var. Okay, so that's how all of those pieces go together. I mentioned another method using a power analyzer. That is a fancy instrument that will give you a reading that looks like this. It will have the real imaginary axes. The voltage vector would be displayed like so, as 277 volts at a phase angle of 0 degrees. And our current vector would be displayed like this, as 10 amps at a phase angle of negative 26 degrees. And these power analyzers typically have a little bit of intelligence, so with the push of a button, it would automatically generate the P, Q, and S values for you. While we're talking about the power analyzer, you'll notice that the voltage vector is on the real axis. That's what's known as the reference vector. Let's work one more example and then call it a day. For this particular problem, we want to find the vector S describing the complex power of the circuit. We start by calculating the total impedance. In this case, it's 0.1 plus 5 in parallel with J10 in parallel with negative J20. So the total impedance, I think we've worked enough of these on your calculators that you guys can do these. So 5 inverse plus, use the parentheses, 10J invert plus parenthesis negative 20J, close the parenthesis, invert equals invert equals. All right, so this is the calculation for this piece. Now we need to add plus 0.1. There we go. That is the total impedance. So 4.8 plus J 1.18. And that is in ohms. The current is equal to a voltage. So 208 divided by an impedance. So that's 208 divided by 4.8 plus 1.18J. Whoops. Plus 1.18J. And polar. So the current is 42 amps at a phase angle of negative 14 degrees. Complex power is the complex conjugate of I by the voltage. Complex power is our current, 42, phase angle of 14 degrees. You'll notice that our current has a negative angle, but in this case, we're using the complex conjugate, so it has a positive angle. And we multiply that by 208. We enter that as 42 at a phase angle of 14 by 208. Our complex power is equal to 8500 plus J2100 VA, or if you prefer, polar form. So that is 8700 VA at a phase angle of 14 degrees. Here's the power triangle. So 14 degrees, 8700 VA, 8500 watts, and 2100 VARs. The power factor is equal to the cosine of 14. You could also say the power factor is the ratio of the adjacent angle over the hypotenuse. So these should come out the same. Cosine 14 gives us 0.97, and 8500 divided by 8700 should give you the same number. So it's about 0.98. Again, slight difference, rounding. What if we went back to our original circuit and removed the capacitor? How would that change things? We could talk about an impedance. So Z total is 0.1 plus 5 in parallel with J10. So that's 5 inverse plus pren 10J, close pren, inverse equals, and then we're going to add 0.1 to that. So the answer is 4.1 plus J2. From there, you can calculate the current. So the current is 208 over 4.1 plus J2. 208 divided by pren 4.1 plus 2J gives you, and we want that in polar form, 46 amps and a phase angle of negative 26 degrees. And I think that one's kind of interesting because you'll notice the current was originally 42 amps. Now the current is at 46 amps. You notice the angle was originally at negative 14. Now the angle is at negative 26. It looks like our circuit performance is being degraded. Complex power is equal to the complex conjugate of the current by the voltage. So that is 46 at a phase angle of 26, all by 208. That is 46 at a phase angle of 26 multiplied by 208. So the complex power is, looks like 8600 plus J 4200. And that's VA in polar form. That is 9600 VA at an angle of 26 degrees. If we build the power triangle, you'll see that it's actually larger. This angle is now 26 degrees. The power has increased by 100 watts. The VARs have greatly increased, so now this is 4200. And the volt amps is 9600. So that's volt amps, watts, and VARs. The power factor is equal to the cosine of 26. So cosine 26, which gives us about 90%. I think you'll agree these are some rather interesting results. All we did is we removed the capacitor. And I think this is the first time you've seen in electronics where removing a part causes the circuit to consume more current. I mean, think about that for a moment. We remove the capacitor, and the original current, which was 42 amps, jumps to 46, all because we removed a part in a series parallel circuit. Now, I don't think that's ever happened in any of your studies before. Personally, I think this is absolutely fascinating that this happens. So again, we went to the circuit, we ran the calculations on the left with the capacitor installed. We removed the capacitor and we ran the equations again on the right side of the screen. It's very interesting that the original current of 42 actually increases when you remove the capacitor from the circuit. So the current increases. The power lost, you'll notice the real power went from 8600 watts to 9600 watts. So without the capacitor, the circuit consumes 100 watts more. And then the VARs, you can see, have increased quite a bit, as has the angle. So we went from 14 originally to 26. I think you would agree that that capacitor is doing quite a bit of good for the circuit. And we will come back to it another day. And that's a topic called power factor correction.